Okay, let's move on to our next speaker. I mentioned that heavy oil is also considered an unconventional resource, and our next speaker is Rick Bowersox. He's in my section, the energy and mineral section, and he's got a background in working on heavy oil accumulations in California. So it was only it was a very simple decision to turn him loose on the Western Kentucky heavy oil tar sands, and he has recently completed an assessment of that resource, and he's going to tell us a little bit about what he's been working on in the tar sands.
Thank you, Dave. Right off the bat, I want to carry it into this title because Kenny's going to tell us about renewable resources in a minute, which far outstrip fossil fuels in terms of energy resources. So carrot is an undeveloped petroleum energy resource, and it makes more sense. And then I'm going to do an advertisement. There are 3 KGS reports I put out this year. First one was background history on the tar sands development that takes care of the rock asphalt industry from 1888 to 1957. That was done to keep straight where samples were coming from, where analyses were coming from, that get folded into the one in Grayson County, which is where the rock asphalt industry started in the state, and then into the larger evaluation of all the tar sand resources in western Kentucky. So, I got to step around here and look at this. The tar sands form a belt extending from Grayson, actually Breckenridge in the north, down to Logan County south, in 3 zones. First 2, whoops, wrong button. So, there we go. The first 2, Big Clifty and Hardinsburg sands, or Lake Mississippian sands. The Caseyville is the early Pennsylvanian that erodes down into these 2. Of these 3 zones, Big Clifty has the single largest resources. Now I'll get to that towards the end here. Caseyville is second, and Hardinsburg underlies or it sets right on top of the Big Clifty in this belt. And there really, comparatively, is not as much there. It's much thinner and be much harder to produce. Industry started in Grayson County. 1888, Dr. Brayfogle out of Louisville opened the first mine, the American Bituminous Rock Company. He closed that in the mid-1890s. It was reopened briefly in the early 1900s, closed again. But Grayson County and then an adjacent part of Hardin County produced rock asphalt up until World War II. Most of the rock asphalt production was in Edmonson County. This is out of the Caseyville, right there in central Grayson County. And then down in Logan County, beginning in 1897 up to just off the advent of World War I, there was one rock asphalt company that produced there near Russellville. If we look at the LiDAR that's available on the KGS Geological map portal, you can get 5-foot LiDAR. And you can see the environmental damage that was done, just the holes in the ground that were left behind by this operation, including right there you can see the mine shafts from the original rock asphalt mining done in the late 1800s, early 1900s. A lot of it in central Grayson County, central Edmonton again, where the biggest mines were, and then in Logan County you can see the original pits. And then a lot of places where they dug around looking for the quality of the ore body there. So the history looks like this. Out of Big Clifty in Grayson County, now in Logan County, this is color coded. The blue is in Caseyville, this is Edmonson County with a little bit that came out of Grayson County late in the development. Total, say about 6 million tons is what I was able to estimate was produced out of this, which produced about 2.3 million barrels of heavy oil and bitumen. Now bitumen, I'm going to mention this a lot. Bitumen is a solid or semi-solid hydrocarbon that when I was in the oil business in California, is stuff we did not want because all it does, it gets heated up, it melts, gets into all the tubing and flow lines, and then it cools off and solidifies, and now you gotta clean this out. Most of what's in the Kentucky tar sands is bitumen. Peaked during the late 1920s, early 1930s. Depression pretty much killed off the biggest part of this industry. Afterwards, this is really Kentucky Rock Asphalt Company and its subsidiaries that produced until 1957. What ended this production was petroleum. Cheap petroleum road mix. The engineers love it because you can control the properties of it, what was in it. That killed off the rock asphalt industry because it's a natural product. From batch to batch, there's a lot of irregularities in the bitumen content. It's hard to lay, get to stay down. The petroleum pretty much ended that. So, everything I did based on prior evaluations, going back to the 1950s, and most recently by Preston and Green in the 1970s, and MC Nogert in the 1980s from KGS. There's a lot of controversy about some of the details about where the tar sands came from and why the only successful economic process for developing has been to dig it out of the ground and build roads that I addressed in this report. And I can explain now why these things, later tests didn't work. One of the controversy is what the source rock was. Well, it's unquestionably the New Albany Shale, western Kentucky. The diacetic partitioning, as the oil migrated into the rock, it actually caused deposition of calcite, which partitioned off the reservoir. It makes it difficult to go in and then do, say, a conventional oil and gas enhanced oil recovery project. How did it become tar sands? Microbes. Microbes can live a long time in the subsurface, and when the oil migrated in the reservoir, it was opened up a buffet, and they turned conventional oil into sludge. When I was in the oil biz and we did water floods, we had to treat all the water that went in the ground with a biocide to make sure no bacteria would get down there and start munching on the oil and turn it into sludge around the well bores. Something that's real important is that reservoirs are oil wet. That's because the bitumen formed up here coats the oil grains. This makes for a lot of oil in place, but very little of that mobile and producible. And then last, they're undersaturated in water, which means that although you can look at core analysis and say, wow, there's a lot of oil here, and the water's here, you add the two of them together, that should come up to 100%, but something less than 100%. That less than 100% is not oil that was lost. This is heavy oil, it doesn't evaporate, it won't oxidize. So what is that 100%? The rest of that to 100%, it's low pressure methane. We'll start with, let's step through these. Source rock. Hooked down in the Albany Shale, moved vertically along faults, accumulated then into the Big Clifty and Hardisburg. The Caseyville eroded down into that, so a lot of oil leaked out of the Hardisburg and up into the Caseyville. And those were deposits that were primarily the rock asphalt produced out of Atkinson County. Look at a core. This is a plug for our display this afternoon that Dave Williams and I will be hosting. You see the nice black bitumen saturated intervals, and then these white areas. I'm just going to show up with the laser. That's calcite that was deposited as the oil moved in. It's actually a fluid that will reduce the chemical environment into a calcite deposited and then partitioning that reservoir. It's something that's not easy to see on logs, and it's expensive to drill cores. This is the extent of the Big Clifty, the single largest resource. What's not shown on this and why the second report on the list is the part up here in Grayson County. Again, again, most of the old tar sands are in central Edmonson County. The best in Big Clifty is actually in Butler County, where it's up to 50 feet thick. It's got the best saturation set. And then back out in Logan County, we're back looking at surface deposits that the only successful way of producing has been to mine it to make road topping. This is what oil wet versus water wet does for you. When I worked in California, those reservoirs, it's heavy oil, but they're water wet, which means that the sand grains are coated with water, so the oil is free to move in the porosity in the middle of this. So you can get the oil out by using conventional thermal processes. That started in the late 1960s, so there's a long history of using thermal enhanced oil recovery processes to produce heavy oil. This is Canada, the Canada tar sands, the Utah tar sands, are water wet reservoirs. You can get that heavy oil and bitumen out using hot water. Ours are like the deposits in western Missouri. There's oil wet. When the oil was biodegraded, it coated and stuck to the sand grains. And about 60% of the total oil in place in the tar sands is there. It's attached to sand grains. Extremely difficult to separate from, get that oil loose, that bitumen loose from the sand grains. It leaves only a fraction of the oil as mobile oil in the pore space, and to make things even worse than what tar sands is, that also includes low pressure methane. Now, core analysis, if you compare analysis where you extract whatever mobile oil is in there to the total porosity, which is total porosity here, and then the vertical axis is the porosity measured after the extraction of the mobile oil and water. You can see that the porosity, the bitumen, part of the porosity that has the bitumen attached to it is much lower than the total porosity. When it's fooled, producers and core labs over the years with this is that the standard process for measuring oil saturation in rock is you heat it up, run a solvent through it, and measure all the oil that comes out. And measure the water, and then you find out it doesn't add up to 100%. There was one operator in Western Kentucky that actually did this testing. At the same time, they were putting in a thermal EOR project using a fire flood where they're actually igniting the reservoir to heat the oil up and bring it out to the producing wells. From what I can tell, they learned that although we're going to produce some oil out of this, we're never going to get anywhere close to what's there total that's in place, and the cost of this makes it prohibitive to continue this process. Technical success, economic failure. The undersaturated part. When the oil migrated into the reservoir back about the early part of the Triassic, we had nice light oil, same green oil we produced out of the deep reservoirs in western Kentucky. We had water. In my example here, I said, okay, let's just make it 50-50. It's easy to do the math. And then methane dissolved in the water part of this. Well, sometime around Middle Cretaceous, western Kentucky was uplifted. Well, when they uplifted the rock, porosity expands because you've taken pressure off of it, but also the temperature drops, so the water fraction that's in the porosity shrinks, and what's left over, so the difference between 10% and 13% porosity because of the uplift fills up with this low pressure methane that was dissolved in water over here. There are actually a few gas wells in Butler County coming out of the Big Clifty with as a gas cap on top of tar sands. And some of the cores that were cut, there's some photographs of gas bubbling out of the core, that low pressure methane bubbling out of the cores, and descriptions of oil and gas bubbles on the core surfaces. If you're going to do a thermal EOR project, and you're gonna inject steam like we did in California, the first thing you have to do is fill that up, that space where the low pressure methane is. All that steam you're gonna inject is preferentially when you fill up that part of the porosity, which means nothing's gonna happen for a very long time, if anything at all. Graphically, this assumes saturation's up to 100%. Bitumen, this is one well that out of a group that measured before and after oil extraction. You can see the bitumen takes up a big chunk of the porosity. The low pressure gas takes up a big chunk of porosity. It's not filled with bitumen. And then if it was filled to a 100%, the rest would be water. The green part, the mobile oil, isn't all that much. Works out to about 40% of the total oil in place is mobile oil that's actually producible. A really good thermal EOR project is going to get between half and 2/3 of that. So 3.36 billion barrels total in place. This is why I wanted to carry it in the undeveloped part, petroleum. Mostly Big Clifty, 2.26 billion barrels. Next to Caseyville, this is largely the surface area in central Edmonton County, and a small amount in the Hardisburg, which is overlying the Big Clifty for the most part. They say about 40% of this is mobile producible oil. If you had a good thermal EOR project, you might get half to 2/3 of that. But this is what happens. 6,300 barrels per acre on average. The best parts were about 20,000 barrels per acre. Thermal EOR projects typically are producing out of 1 acre patterns with anywhere from 4 to 6 wells. An efficient one, 4 to 6 producing wells with 1 steam injector, or in a fire flood, 1 oxygen injector in the middle of that. Well, we do the math, and say 20,000 barrels per acre, 40% of that's producible, so about, 8,000 barrels is producible. Recover about half of that, you got 4,000 barrels. At $100 a barrel, you get $400,000. With oil prices aren't $100 a barrel, and even at $100 a barrel, you have to recover your capital costs, operating costs, taxes, royalties to the landowner, and just doesn't, the math doesn't work. So that's the problem with our tar sands. It's likely going to continue that. The math isn't going to work going with conventional oil and gas development. So at this point, digging it up and somehow extracting the oil would be about the best way to produce it. And that limits you to parts of Logan County, central Edmonton County, and parts of Grayson County. And most of this then will be undeveloped and undevelopable. So, thank you very much. I'll entertain any questions about this. Now, those 3 articles, I will tell you, those 3 publications explain what I've quickly gone through here in excruciating detail. So, and I make no bones that 2 of those are pretty technical, but it does explain what all this means and the effects of what's happened in the reservoir history to make it where we are, to get to where we are today. So thank you very much.